Uh, I need the equations for all of them. The report sheet's going to look like this. All you're going to do is you're going to list the cations that you found in your unknown. So your unknown is just going to be just, for the cation unknown, let's say you found sodium and potassium. And then for your anion unknown, let's say you found whatever, sulfate. And then the part 2 of the report is the known. The known, you had everything in there, right? And so I want everything in there. And so your points are going to be spread out over your known and your unknown.
So for the first page, you just want us to list the anion Chem. You don't need your observation.
You don't need to write anything, observations or whatever. You need your unknown number. Unknown number had these ions, right? But you have to write down the observations and equations, the simple ones that I wrote on the board for all the ions. Yeah, and so you do the known cations and then the known anions. So there are going to be 10 cations if you're going to write out, and then the number of anions.
But we don't have to write observations. We just say like sodium and then like the.
No, you have to write simple observations. Like for example, sodium would be unknown AQ plus flame yields yellow, flame. That's what I mean by observation. You write simple observations like that, and then the equations associated with that for every ion. This is to help distribute the points, because let's say you're unknown, you got every single ion wrong, then all your observations and equations are going to be wrong because those are wrong, right? You're going to lose a huge amount of points, which, I can't, this is the exact scenario that I've had in the past. And a long time ago, I had people just write the observations and equations for the unknown, but when they got it wrong, and some people get it terribly wrong, they get 0 points on this. Essentially, they get points for just participation, but it's not that much.
What if you didn't do the anions almost equations?
Yeah, that way you could get more points. If you didn't do the anions and you write the observation and equations for that, then you can get some points for that. That's fine.
And that's how it works. So not if we got the anions correct.
No, even if you get the anions correct or anions wrong, you should write out all the observations and equations for that. This is what you should have gotten had you had chloride, had you had bromide. That's what you would have gotten. Okay.
It doesn't need to be typed.
It doesn't need to be typed. Actually, it doesn't need to be typed, but the reports I've seen so far have been typed. So, it can be typed if you want. Okay. Some people are just faster typing than writing. So. But either way, I don't care. And I don't want to see condensed observations. They say, you know what, I just did that in the previous, so I'm going to skip that in this one. No. It's very simple. This shouldn't be so hard. But it is hard. Every semester it's hard. It's hard because every semester I ask for the same thing, which is write down all the observations and equations, and then every semester, lots of people don't write down all of them. They write down half of them. They write down a third of them. Every semester I said, just copy down what I wrote on the board. And then every semester people write the most weird stuff. I don't know what they're writing, it should be simple, easy points. Everybody should be able to get 100% on this. But, only about, maybe about 70%, 60 to 70% of the class get 100%, and then 30% lose a lot of points, usually. Fine. The unknown though, yeah, hopefully you get 100%. You know, it's a much smaller percentage that gets 100% on the unknown. Like 40. Still, it's decent though. Depends on the semester. All right, other questions on that? Does that answer the question about the unknown?
Are these points separate? So like, or is it just one whole?
One whole thing. Yeah.
When is the due?
Tuesday.
Was it Thursday?
It was officially due tomorrow. If you have it done, just turn it in. Some people have already finished it. They had it done yesterday. They wanted to turn it in, but I try to collect them all at once, so I don't file them in different places. So. But if you have yours done tomorrow, turn it in. All right, other questions? On 65 through 70 on the homework? Oh, the structure and acid strength? You can skip those. I don't know if it's 65, whatever that was, the sections that deal with structure and acid strength. You know, which one's a stronger acid? This or this? Those ones you can skip. Or what's a stronger base, oxide or sulfide? You know, let's skip that. Okay, other questions? How about from the practice test? Are there any questions from that? This is James posted that. That was actually from 2 years ago, that test. So. But that's fine. It's you know, it's going to be comparable. Uh-huh.
What does
Sorry.
LCAO stand for?
LCAO stands for linear combination of atomic orbitals. Do you remember doing this in Chem 1A? A 1s orbital on atom A, a 1s orbital on atom B, and then you do an LCAO to generate something called a sigma 1s orbital, which looks like that, and a sigma star 1s orbital, which looks like that. These are MOs, these are AOs. And so we do LCAO, LC, linear combination of AOs to generate MOs. That's what LCAO stands for. HSAB, does somebody remember what HSAB stands for? Hard soft acid bases. And so what somebody did, actually this professor at UCSB who originally developed the idea of HSAB, at the time he wasn't at UCSB, before I think he was at Michigan. But he came up with HSAB to try to put this into terms that might be more useful. And so LCAO and HSAB, LCAO is in Chem 1A. HSAB is not in Chem 1A. HSAB was in the PowerPoint that showed in the first week of class. But I didn't give you an example of HSAB. Let me give you an example of HSAB. If you take a 1s orbital and let's say a 2p orbital like this, you know, and do an LCAO, 2p orbital should be bigger. That's going to form MOs, right? But if you take a 1s orbital and a 4p orbital, that's also going to form MOs. And so what HSAB does is it looks at this. This would be a good combination because 1s we call a hard, a little 2p would be hard. And so hard, hard, is good. But a 4p would be soft. It's more polarizable. It's bigger electron cloud. You guys remember about polarizability and electron clouds? That kind of stuff from Chem 1A. And so we call this soft. And so 1s and a 4p aren't going to form as good of MOs as a 1s and a 2p. However, if you have, let's say, a 4s and a 4p, a 4s and a 2p, is that good? No, this is what we call soft hard. But a 4s and a 4p, that's good. 4s and a 4p is good. Soft, soft. So hard, hard, soft, soft make the best linear combination of AOs. Why do we need that? Why did I even bother talking about this Chem 1A stuff in Chem 1B? Acid strength. If you look at all acids in nature, true or false, are Bronsted acids. All acids are Bronsted. That's false, right? All acids in nature are Lewis acids. True or false? That's true. That's true. And so what we need is an acid chart that tells us the strength of acids, right? Which was a stronger acid. But the problem is that is too complicated. Why? That's too complicated because we need to know LCAO and HSAB. And so instead of doing that, what we do is we take all acids and then just take a subcategory of the acids. We just look at some of the acids, not all the acids, and ignore the other acids. This subcategory of acids that we look at are called the Bronsted acids and bases. The Bronsted acids and bases, predicting acid strength is very easy because we have a Bronsted acid-base chart here, and it's easy to predict what's a stronger acid and what's a weaker acid just by looking at the chart, right? We can look for patterns in the chart. The patterns in the chart are what we see when we look at, section 16.7 and 16.8. And so for Bronsted, it's easy because the acid is always the same. The acid is always H+, but in Lewis, the acid doesn't always have to be H. The acid can be lots of different atoms, meaning that all of a sudden things get a heck of a lot more complicated because if your acid is always H+, then all you're looking at is base. What kind of base are you attacking with? So spending all that time talking about LCAO and HSAB earlier was because of trying to predict acid strength.
So can you give an example of a Lewis acid that doesn't have an H in it?
A Lewis acid that doesn't have an H? I could give you a lot of examples of Lewis acids that don't have H in it.
Isn't the silver like
BF3 is a very powerful acid. This is a strong acid. Does it look like a strong acid to you? No. CO2 is a weaker acid. Much weaker acid. CO2 is a much weaker acid. Well, BF3 is easy. CO2 is a little bit more complex. BF3 is easy because it has less than an octet. It's only got 6 electrons there.
What's the conjugate base for BF3?
What's the conjugate base? Well, in Lewis acid-base reactions, you form what we call Lewis acid-base adduct. Conjugate acids and bases we use in Bronsted to understand it because the acids are the same, and therefore we're going to get the conjugate base. But in this here, what we form is So let's use a Lewis base like ammonia, which is also a Bronsted base too, and we form this. So what is the Lewis conjugate base of this? And so if we were to reverse this reaction, then what we look for is a base is an electron pair donor, right? And an acid is electron pair acceptor. But do you see an electron pair that we can donate? No, I see a bonding pair here. And so in one sense, a boron takes its bonding pair and loses it to nitrogen. So nitrogen is the acceptor, but this is not exactly what we think of when we think of a Lewis acid-base reaction. So the whole concept that we typically think of in terms of Bronsted is different for this, is more complicated. You know, you look at the aluminum, you know, hexaaqua aluminum. Water is the base, and aluminum 3+ is the acid. And so what's the conjugate? So we don't think in that way. Don't worry about that. I'm not going to ask you. So in Lewis acid-base reactions, we do these mechanistically. And so, like this. And so at the first level, we just look at, you know, how the electron pairs move around. But as you get into, if you're going to organic chemistry, then you start thinking not just how the electron pairs, but you also look at the orbitals. And so you start off simple. You do valence bond theory. Valence bond says that bonds are formed by orbital overlap. But as you get into advanced organic chemistry, or more like second semester organic chemistry, then you start looking at molecular orbitals, seeing how the molecular orbitals are arranged in organic. And so probably second semester, you're going to get into MOs in organic. Because MOs are very important because, especially in biological systems, because in biological systems, you know, the three-dimensional structure plays a huge role in the reactivity of these molecules. Three-dimensional structures can be dictated by the orbitals, right, that are present. But not just biological systems, but even in like catalysis or industrial processes, you know, it's very important, these types of orbital interactions. So why start talking about it now? Because, you know, when you get to organic, you don't want to be, you know, what's that? You know, so, yeah, I guess I didn't really have to bring it up, but it's better, you know, if you hear it repeatedly rather than, you know, all of a sudden you're hit with this. Yeah.
Is there a cutoff for hard and soft?
Hard, soft, yeah, you know, hard, soft is just all qualitative. There's no cutoff, you know. You just look, is it kind of big, squishy, or is it kind of hard, you know, dense, you know, that kind of thing, as far as electron cloud goes. There's no real cutoff. If you look at the tables, you know, what he did was, this professor that came up with this, HSAB, he generated a whole bunch of tables. Actually, you know, it would be interesting to see. You just do a Google search.
Would you consider 3P hard or soft?
Depends on what you react it with, you know, but 3P, maybe that's borderline. You know, it's just relative. It's relative to what you're reacting with. And so 3P could be hard if you're reacting with some big one, like 7P or whatever else, you know, or it could be soft if you're reacting with a small one, like a 2P, you know. It's all relative depending on what you're reacting with. And so, it is, in that sense, it depends. That's why the answer to the question on the practice exam was what? Well, anyway, Or maybe you haven't gotten there. Yeah. So.
So then, were the 4P, like, in that example, you said 4P was soft. If we combined it with, let's say like a 9P,
No,
or 9S.
no, then it would be hard. You know, it's all, you know, it's softer relative to, so I set the framework. The framework was a 1s orbital. In terms of a 1s orbital, what's hard and what's soft, you know? That's it. Things like, certain metals have a high affinity for sulfur, like heavy metals. Heavy metals have a high affinity because heavy metals are soft, sulfur's soft, right? Compared to, it's like oxygen. All right, here we have some organic acids here. Here we could look at the hardness and softness, you know, that they give of carbon in these acids. And so we have these a whole bunch of different organic acids. This HSAB is going to be more important for you in organic chemistry than for us. We aren't going to do anything with it. Well, a lot of you aren't taking organic chemistry. But, you know, it's important, all this orbital stuff. Let's see. I wish they had a more comprehensive list. For us, we would look at things like ligands and essential metals or whatever. In organic chemistry, they call bases nucleophiles because they're after like nucleus positive charge. And they call acids electrophiles in organic chemistry. So we call them ligands and essential metals or whatever else. And then when we look at these nucleophiles and electrophiles, here we can see some classification for Lewis acids. Class A are core, and so this is in context of, this looks like, oh, actually this is both organics and inorganics here. Some class B Lewis acids here, which are the soft, so just hard and soft. And so here they have a dividing line here in terms of that. And so with HSAB, we try to understand all acids, not just the Bronsted acids. But for us, it's too much. So we just do a little subset of the acids. Look how many, you recognize a lot of these acids? Now, some of these are super acids, but you don't recognize a lot of them, do you? If you go into organic, you'll probably recognize a lot more, you know? But for us, this is beyond.
So as the charge increases, does
Acidity,
the hard-
yeah, the hardness increases, right. Yeah. Yeah, like a sodium +1 is considered pretty soft. Or maybe it's hard, I don't know. Let's see here. Oh, sodium +1 is considered hard. But a silver +1 is considered soft. Silver is a heavy metal. Soft.
why is it that as charge increases obviously?
Usually we think of that just in terms of polarizability, you know, and charge density. You know, when you look at the like fluoride versus bromide, you know, which one would be softer, which one would be harder? Fluoride or bromide? Well, fluoride and bromide aren't on this because it would be Lewis bases. Let's see, do they have a Lewis base thing here? Which one would you guess would be harder, fluoride or bromide? Fluoride, because it's smaller, the charge density is more dense. You know, Whereas bromide's big, got big orbitals, the charge density is spread out thinly. You know, it's soft, it's polarizable. Bromine versus iodine, you know, you learn about polarizability in terms of dispersion or London forces, right? Iodine's big and polarizable, bromine's gonna be smaller and less polarizable. And so in terms of hardness and softness, then iodine would be softer, bromine would be harder.
Why is it that heavy metals have high affinity for sulfur?
Because sulfur's soft. Sulfur's soft. And so sulfur is contained in some proteins, and so heavy metals attack that, bind to the protein, and cause the protein to become denatured, or whatever they call it. In other words, screw it up.
So relative to sulfur and high heavy metals are soft.
Yeah, heavy metals are soft. Sulfur is soft. Is this it? Pearson is his name. There it is. So anyway, like I said, in organic you're going to get into, this is a lot more important. The hard, soft, acid, base, HSAB principle, and organic chemistry, an overview of that. And so, in organic, you look at these, you know, what we call the reaction mechanisms, and it's all this acid-base type stuff. A lot of it is. You know, there are other types of mechanisms as well, like free radicals and this type, but you know, you're always looking at how the electrons are rearranging in these structures. Oh, this is an interesting review here. And so here we can see fluoride, hard, iodide, soft. That's it. And so fluoride likes to react with hard acids. Iodide likes to react with soft. It's very, so trying to take all this complex quantum mechanics and then try to simplify it into something you can use without having to do calculations, computer calculations, because the equations of quantum mechanics, the Schrodinger equation is too hard to solve
So
without
how do you
approximations.
mix solution that contains fluoride and hydrofluoric acid?
Boron, what?
No, hydrofluoric
Hydrofluoric acid and
and some fluoride.
chloride ions? Fluoride ions? If you mix hydrofluoric acid with fluoride ions, you got what's called a buffer, a Henderson-Hasselbalch buffer. And so a mixture of HF and fluoride is a stable solution. This is what we call a weak acid. This is a weak base. And so if we take a weak acid and weak base and mix them together, I forgot how far I got with weak acid, weak base mixtures. They don't neutralize each other out. In fact, this one, they can't neutralize each other out because, you know, if they react with each other, they're going to form HF and fluoride. And so it looks like no reaction. And so we're going to look at this today. Weak acid, weak base mixture. So this one we would just consider Bronsted because it's easier. You know, proton donor, proton acceptor. The Lewis ones are usually, you know, or the ones that don't look like an acid. Look at all these acids. Do any of them look like an acid? Look at all these acids. None of these are Bronsted except for here. Here's our Bronsted acid. Bronsted acids are formed H-bonded molecules. It's like, okay, here's your borderline region, borderline here. So yeah, I guess there is a border here. And I just forgot about it. Here's some borderline ones here. And the bases, hard and soft. But it's still kind of relative because if you look at most of these,
So borderlines have
No, borderlines are kind of, what do you call, you know, if a 2P is hard and a 4P is soft, what do you call a 3P? You know, that's borderline. Or something like that. But it's still, it depends on what you react it with, so you look at it case by case. Anyway, this is a lot of talk about this stuff. And the reason is the take-home point of all that talk about this stuff was what? And I said this take-home point a number of times. Is there a table that lists the strength of? No. Only for a small subset, which are the Bronsted. And that was the take-home point. So you don't need to know the theory and who derived it. You know, Ralph Pearson is the person who came up with hard, soft, acid, base. You don't need to know the year or that type of stuff. Let me see what they say about Ralph Pearson. Yeah, also known as Pearson acid-base concept, developed in the 1960s. I've met Ralph Pearson. Maybe that's why I bother talking about HSAB, because probably nobody else bothers to talk about it in general chem, you know. But I figured, yeah, since we're talking about acids and bases, we need to talk about HSAB. You know, it's because it's so important. And everybody should know LCAO from Chem 1A, but lots of people forget. You know, when I was a student, you know, I was taking physical chemistry, and one of the questions was, you know, what's the Heisenberg uncertainty principle? You know, a lot of people forgot the Heisenberg. Do you guys remember the Heisenberg uncertainty principle? What? Look it up. And so, why did people forget the Heisenberg uncertainty? They haven't heard it, and so repetition's good. So let's start the repetition now. Well, some people ask me, you know, why did I introduce common ion in chapter 16 when it's talked about in chapter 17? Well, it's talked about in chapter 17, but it started in chapter 16, so that's why. And I figure more repetition is better. All right, any other questions on the test? Practice, the old test? I don't know if I should call it practice test. Some people hate that word, practice test, because they think I'm, you know, teaching to the test. Maybe. The reason why I make it available is because, you know, when I was taking physical chemistry at UCLA, there was a star athlete in my class. The star athlete would only show up for the exams. And I thought, you know, how could a person just show up for the exams and manage to do okay in the class? And so I looked into it more. The star athlete had access to all the old exams, which I didn't have, and tutors and a whole bunch of other stuff. So then I thought, that's not fair. We should, you know, if the old exams are available, they should be available for everybody, not just the star athletes. And so that's why I post the old exam, because I never thought that was fair. Not that we have star athletes here that get special treatment. Probably the athletes here get no special treatment at all, right? Uh-huh.
How do we know which space is stronger? For the question.
How do you know? That was the whole point of this. How do you know? How do you know which Lewis acid base is stronger? Well, you have to use LCAO and HSAB. All right, so use it.
So we look at the
Yeah. Right, but there's something important missing. If your acid, if your base is soft or hard, what are you reacting it with? You got to look at what acid you're reacting with it, right? Soft like soft, hard like hard. And so what's the acid?
It just says which Lewis base is stronger, OH3 or OH2.
And so the whole point of all this is that it depends on the acid. How do you know what the acid is, you know? If the acid's hard, then okay, you know? But even if both of those are hard, let's say hydroxide and ammonia, both of those are hard, then we got to look, you know, which one has a better LCAO. So anyway, what you should do with all these concepts is write like a little take-home message. You know, why was I talking about LCAO and HSAB? What was the point? If the point is not clear, you know, and I don't, maybe I tell you the point, but I don't specifically say this is the point of all this, right? Because, you know, the points, the way you remember the points is you come up with them yourself. That's the way, and if it's in your own words rather than me telling you, because I didn't tell you just once, I told you multiple times, but the thing is, it doesn't stick, because memorizing somebody else's words just doesn't work that effectively. If you sit down there, and this is why I always say annotate your notes. When you annotate your notes, you're annotating it like this is the take-home message I got from this. And then what you do is you verify this, you know, in class or in office hours or somewhere else. You know, was the point of all this? You know, did I get it right? And then when you go into the exam, you know what you do is, this is called data reduction in science. You take all this information and then you try to reduce it into simple points, you know? And this is the whole process of learning, because if somebody just tells you the simple point and you just memorize it, then it's not the same. It's not the same as formulating that in your mind. And it doesn't have the same depth, because if you get something outside, you know, and you came up with this point, then you say, okay, this is a slight variation to that, you can figure it out. Whereas if you just memorize the take-home message, then it's very shallow. And so the whole point of all that stuff was that Lewis acids and bases are complicated. And in order to understand which one's stronger, you have to know both. And you have to know HSAB. And so that's what the whole PowerPoint thing was at the beginning of the semester. The point was there in the PowerPoint.
The highest pH possible is not infinity.
No, it can't be infinity, right? And what would be the concentration of hydroxide at a pH of infinity? It'd be 10 to the infinity power. Yeah, it's impossible. Even though mathematically, yeah, we could do that. 10 to the infinity power approaching infinity. And so, yeah. But in terms of chemical, you got to know not just the numbers, but you got to know what the numbers mean. In Chem 1A, this always happens. You know, there's a joke in the department about this. You know, a lot of people say, well, the density of water is 420 grams per milliliter. There's kind of a running joke about this, because what is the density of gold? The density of gold is 20 grams per milliliter. And so somebody getting a density of water 420, because that's what the chart said, it's a ridiculous number. So you have to know certain numbers, you know, are going to be ridiculous. And so something like that is a ridiculous number. You cannot get that kind of hydroxide concentration. You got to look at solubility and other things. Right? Unfortunately, the equation doesn't tell you that, because, the molarity of hydronium is equal to 10 to the minus pH molar. And so this is going to be 10 to the minus infinity molar. Therefore, that's the answer. Mathematically, yeah, that's the answer. That's correct, but the equation doesn't tell you, you know, that you can't do that in reality. Mm-hmm.
Was the
temperature and pH? The relationship is complicated, and so this is something else you should have gotten. The relationship is complicated because we have pH. pH changes with temperature, right? pH changes with temperature. So if you're measuring the pH of water, at 25 degrees C, it's pH 7. At another temperature, it's not pH 7 any longer. But it's just water. It's still pure water. That's a headache. And so what people do is they use meters that compensate for the temperature. The old style meters have a little knob on the front of the pH meter. So no matter what the temperature of the water is, they dial the knob so that it's always 7. And so the pH of water is always 7, right? At any temperature. But in reality, it's not the case. In reality, the pH changes, and we just use electronics to reset it at 7. And so to answer that question is, it depends. If you're using a pH meter, then yeah, the pH doesn't change with temperature. The pH of water is always 7, right? Pure water. But if you aren't using a pH meter that doesn't have a temperature calibration, then it's going to change. And so what is the relationship? As the temperature goes up, what happens to the pH? No. It goes down. Why? Well, that's the other thing. I drew this with the population versus temp. This is what is this? This is population versus kinetic energy. Long time ago. I didn't, I did this a long time ago talking about the collisions of water. This is called a kinetic energy distribution, or speed distribution in Chem 1A. So we talk about this. What happens to this distribution as the temperature goes up? Yeah, and so we can see, if this is water, do all water molecules at 25 degrees C have the same kinetic energy? The answer is no. Right? They're all going to have the same average kinetic energy, but not the same kinetic energy. So as the temperature goes up, the average kinetic energy goes up. As the average kinetic energy goes up, then more molecules will have enough energy to break bonds, which means the hydronium ion concentration increases. As the hydronium ion concentration increases, the pH decreases. And so there are two answers to that question. One answer is the pH doesn't change because we have a temperature calibration on a pH meter. And the lab, the temperature is fluctuating. Even during the day, the temperature fluctuates. If you have to, look at that, you're going to be in for a headache. This is why people like molality instead of molarity. One of the differences between molality and molarity doesn't depend on temperature. Molarity changes with temperature. All right, what else do you have questions about? Uh-huh. A problem? Which problem? Problem 16 on what?
On the practice,
On the old exam? Well, it's supposed to be practice, or mock, or whatever. And so if I do the problem, it's just like... Then it kind of defeats the purpose of this, because the purpose of this is to take it as a test. What was the 16 anyway? What was the problem?
Determine the pH of 1.00 times 10 to the 7th hydrochloric acid.
Oh, the pH is easy. pH is 7. Right? It's 10 to the minus 7 molar hydrochloric acid, so therefore the pH is 7. It's going to be 10 to the minus 7 molar hydronium. It's easy. And so maybe about 10 or 15% of the class put pH 7 on this. This was in 2013. pH 7. Right. But unfortunately, the pH 7 is the wrong answer. pH 7, because you're adding acid. Adding acid to the water should make it more acidic, not stay neutral. And so, even though it's probably a small drop in pH, we should still factor that in. And so, I don't want to do this one because I did something very similar to this. Do you recall which one it was? We started the chapter with this problem. What was it? Yeah, 1.0 times 10 to the negative 8 molar HCl. You did that as the first problem. And so your hint here is use that problem as a model for this problem. Not only should you annotate your notes with some kind of like take-home message, you know, for this, it's all part of this data reduction process, or all part of the learning process.
So you would recommend that one we solve stepwise?
No, I recommend you solve every problem stepwise,
Oh, okay.
and then see if it fails. Every single problem we try, we do because, you know, if you try to solve every problem simultaneously, which you should solve every problem simultaneously. How much time is that going to take, right? And solving simultaneously, as you saw, is not easy, right? Solving simultaneous equilibria is a big pain, so we try to avoid that as much as possible. We try to avoid it by using alternate techniques like stepwise. If stepwise works, then we would have gotten pretty much the same answer doing it simultaneously. Or, as we'll see in chapter 18, combined. But even if you have to do it simultaneously, some people can do it quite quickly. You know, some people are pretty good at math, and they'll zip right through it. But you don't have to, because for our class, you just have to recognize that stepwise failed and it must be solved simultaneously, and then that's full credit. Anything beyond that would be extra credit. And so, yeah, that one you would try solving simultaneous. I mean, not simultaneous. You don't want to try solving any problem simultaneously to start. I'm going to try it solving stepwise. Some problems you immediately recognize whether they're simultaneous or stepwise, you know, by looking at the K's or the molarities, or both K's and molarities. But for tests, you know, I don't want you to say, oh, I just looked at it and it must be solved simultaneously. I want you to show me why stepwise failed, and you must solve it simultaneously. For HCl, stepwise is going to work. Why? Yeah, for step 1, nothing can perturb step 1. K is very large. Okay.
So when K is very large, stepwise.
When K is very large, nothing can perturb that step. Subsequent steps might screw things up. So if I had something like some acid, that's a very unusual acid. With a pretty big first K, but subsequent steps. Actually, I can't think of any right now. But yeah, pretty much. All right, other things. So that one, just look at what we did with the 10 to the minus 8 molar HCl. It's pretty much the same. Let me tell you, it's going to be the same. If the molarity is large enough, can you use stepwise? Don't even think about that. Just try stepwise and see if it works. Because if the molarity is large, can you do it stepwise? Not always, because it depends on the K for step 2. If the molarity is large and the K for step 1 and step 2 are comparable, then that's going to be simultaneous. So let's say step 1 is 10 to the minus 4, step 2 is 10 to the minus 4, 10 to the minus 5. Most likely simultaneous, because both steps are going to be significant, and therefore they're going to perturb one another. Whereas if the first step is 10 to the minus 4 and the second step is like 10 to the minus 9, then it's insignificant, that second step. Now, if the molarity is very small and the like first step is 10 to the minus 8, or let's say no, the first step is 10 to the minus 9, and then the second step is 10 to the minus 14. The molarity is very small. Even though that's 5 orders of magnitude difference, it's probably going to be simultaneous because of the concentrations that we get. Those aren't like hard rules because we look at it case by case. Sometimes it's just obvious though. It's going to be stepwise or simultaneous.
Would you recommend if I look up, because I know that stepwise is like not really on the textbook at all, or if it is, it's not really brought it up, so.
No, stepwise is in the textbook. I just try to come up with the stepwise and simultaneous are my words that I use for this. The book does it. The book does it, but they don't come up with a name for it. And so I just came up with a name so you recognize when the book is using stepwise versus when the book is using simultaneous. And so I wish they would just label it so there isn't as much confusion, because a lot of people think, well, it's not in the book, so if it's not in the book, I'm not going to worry about it. But that just gets them in trouble, because it is in the book. They just don't see it in that way. Okay. And it's my jargon, so you talk to other people. Other people may be quite familiar with this, except they aren't familiar with the words I use for it. And so when you talk to other people about this, then you have to at least be sensitive to that they might not know stepwise and simultaneous because they weren't taught in that way. That's it. And so yeah, somebody was asking me about this. Like the tutor, we have a tutor who's been tutoring with us for many years, and I talked to him, why doesn't he tutor 1B? Because he was my 1A student, but he said he had a different instructor for 1B, and so he's not used to all the words I use for it, and so that's why he says, rather than, I'm sure he knows the techniques, it's just rather than learning all the jargon, just rather not to tutor it. That's it. All right. Any other questions on that? So a lot of mistakes were made on number 16. One, pH 7 2, well, maybe not 16. Fewer mistakes were made. Maybe a lot of mistakes were made on 15 or 17, whatever it was. Okay, if there are no other questions, then we're going to continue with chapter 17 stuff. And chapter 17 deals with acid and base mixtures. And so we're going to look at different mixtures of acids and bases. And so the first mixture we're going to look at is the most complicated mixture. It's the most complicated mixture and that would be a mixture of a weak acid with a weak base. Did I already talk about this?
Yeah,
Did we do potassium aluminum sulfate?
no, we did, acetic acid and ammonia.
We did acetic acid and ammonia? Okay. And so the situation with acetic acid and ammonia was that in order to solve that, we would have to do simultaneous equilibria of what and what and what and what and what and what. If there, I don't know how many there are, but we'd have to do simultaneous equilibria of how many equilibria?
Acetic acid, ammonia, and water.
Well, we would do what? Acetic acid, ammonia, and water? What were the major species after the initial reaction?
Oh, and then we have ammonia.
Ammonium and acetate. Those were the major species. So for sure we do a Ka for ammonium because that has the highest concentration. Kb for acetate. But we also have ammonia and acetic acid. So should we do ammonia, Ka, and, oh no, it wouldn't be Ka for ammonia. It would be Kb and Ka for acetic acid. So that's 4. We got Ka for ammonium, Ka for acetic acid, Kb for ammonia, and Kb for acetate, and then Kw. So altogether 5 equilibria that needs to be solved simultaneously. Is that correct? And so the answer is no. It's actually only 3. Why? It'd be redundant. And so that was, I think that was where we ended up. I was just saying we don't have to do acetic acid and ammonia because those would be redundant with ammonium and acetate. I thought we did potassium aluminum sulfate because
That was in the ammonia.
we didn't do that. Okay. Same thing there. You know, for the lab, we would have to do Ka for aluminum, Kb for sulfate, and Kw. And so, shoot. Did we do ammonium acetate a while back? This would be last week. We did ammonium acetate, and then we saw that Kw was going to perturb the earlier steps. Okay. Well, that's the basic scenario. When you take a weak acid and a weak base, then they're going to perturb, right? And so therefore it must be solved simultaneously. except for two specific types of weak acid, weak base mixtures. Yeah, when the weak acid and weak base are conjugate pairs, we call that a buffer or Henderson-Hasselbalch mixture. Did I talk about that last time? Yeah. And then what was the other scenario? When they're the same species, that's correct. And so, in chapter 17, we're dealing with weak acid, weak base mixtures. Actually, in chapter 17, we're dealing with all acid-base mixtures. You know, whether they're weak or not. And so, the first type of mixture we're going to look at is weak acid plus weak base. And so I showed in ammonium acetate that they're going to perturb each other. And it must be solved simultaneously. And so we have to solve this simultaneously. What does your book say in the homework? I forgot. The book doesn't say they have to solve it simultaneously. In the answer, like they do ammonia with acetic acid. And they say that, this is what I mean by my jargon versus the book's jargon. And so, I'll show you what they say in a minute, but let me just show you one other thing. You know what? Or maybe it doesn't matter. I appreciate that you bear with me because I use my own words for this. This is what the book will say about it. I guess they don't talk about it in the I guess they don't talk about it. You know, that's the most convenient way. Just don't talk about it, and then you don't have to deal with it until you get to the homework, and then it's in the homework. But I guess it's not talked about in the lecture. But that's how to make a homework problem hard. Is just don't talk about it and then throw it out in the homework. But anyway, I thought they did talk about it. It's weird. Okay. Well, this is called a weak acid, weak base titration. Titration is when you mix an acid and base together, right? And so this is another name for mixing acid and base. And so weak acid, weak base titration. Google that and you'll find it. Okay. But these have to be solved simultaneously, unless we have, it's simultaneous unless it's a special mixture. And the special mixture that we're going to have is one, the special mixture will be the acid and base are the same. We call this amphoteric. And then the pH is, we solve it simultaneously. Simultaneous unless a special mixture. So amphoteric, this has to be solved simultaneous too. But because the acid and base are the same thing, it's simplified. It's easier. This has to be solved simultaneous, and from the math, we get a simple equation. From all this math, we end up with that the pH is equal to the pKa1 or pK of the amphoteric species, plus pKa2, which is the conjugate acid of the amphoteric. Divided by 2. And so, yeah, it's solved simultaneous, but we get this simple engineering style equation. And then the other is 2. The acid and base are conjugate pairs. When the acid and base are conjugate pairs, we need not solve this simultaneously. This does not have to be solved simultaneous. And the reason they don't have to be solved simultaneous is, let's look at the example. HF and fluoride is not a good example because HF is very dangerous acid, and too much fluoride is dangerous too, right? And so, yeah, let's do something like this. Let's do acetic acid and sodium acetate. This is different than just having acetic acid. If I just have acetic acid, we call it an acid mixture. But in acetic acid, is there acetate present in acetic acid? Yeah, because acetic acid hydrolyzes water to form hydronium and acetate, right? But this is different because that acetate comes from the hydrolysis of water by acetic acid. This acetate comes from, well, we were making a mixture. So we're going to pour in some acetic acid, we're going to pour in some sodium acetate solution. And so we have a mixture of both present in significant concentrations, right? Versus if this were pure acetic acid, we'd have mostly acetic acid and a tiny bit of acetate, right? Or if this were just sodium acetate, we'd have a lot of acetate and some tiny bit of acetic acid. But here we're going to have significant concentrations of both. So we got weak acid, weak base. And they're conjugates of each other. The reason we don't have to solve this simultaneously is because, somebody tell me, can you see it right off why we don't have to solve this simultaneously? We don't have to solve this simultaneously because over here we have to solve this simultaneously because, like for example, the amphoteric, we have the Ka for the amphoteric and the Kb, and we're going to do both, right? You can't ignore the other, one or the other, right? And the same thing with up here in general, like ammonium acetate. Don't say forward reaction, reverse reaction. You would say, you have to put this in the context of Ka. We're going to have a Ka for this, and we're going to have a Kb for that. And what's special about the Ka and the Kb? The book doesn't use the word redundant, right? But I use the word redundant so that you recognize that this is actually redundant. It's redundant because because Ka for this looks like this. The reason I use the word redundant is I wish the book would come up with a word for this, you know? That we could use that and that you guys could read in the book, right? But since they don't, this is one of those things that they want you to formulate. This is the data reduction part. You look at all these examples in the book and then you come up with a pattern that you see, right? And this is exactly what I did. When I look at the book, this is what I say. This is the take-home point of this. The take-home point is this is redundant, right? And so this is Ka for this. And then Kb for this looks like this. C2H3O2 minus plus H2O liquid. It's going to give us HC2H3O2 plus hydroxide. You look at those two equilibrium, what do you see? Exactly the same thing. The only difference is one, you're going to get the pH, the other, you'll get the POH, but it's the same number. I mean, essentially, you're going to get the same pH for both of these. And so if you were to do both of these, you're wasting your time. You're going in circles because, you know, it's the same thing. You might do both of them because you say the Ka for this is 1.8 times 10 to the minus 5. Well, the Kb for this is equal to the Kw over the Ka for what acid? Well, it's going to be the Ka for acetic acid, H3O2. And when we do that, it comes out to 5. We aren't going to round it. We'll just do 5.55 times 10 to the minus 10. Right? And so you think, okay, you know what? I'm going to just do this first. And so we do the ice table here. This is what we call common ion. And so here, I'm going to go with 0.100. I'm going to say that this solution is 0.100 molar acetic acid, and at the same time, we're going to have it 0.100 molar sodium acetate. And so we have 0.100 molar acetic acid to begin with here, 0.100 molar, and then the acetate is going to be 0.100 molar. And the hydronium is going to be 0. Now take a look at the redundancy here. If we were to do Kb, the acetate is 0.100 molar, and the acetic acid is 0.100 molar, and the hydroxide is 0. Do you see we're going to solve the same thing? Exactly. And so this is redundant. We do one or the other, but not both. One or the other. Well, which one should we do? Well, Ka is bigger, so we probably should do Ka, right? Ka. And so in this case, what we would do is we would just solve this, and then we come up with the hydronium ion concentration. And so this is a special mixture that doesn't require anything. It just requires a regular ice table. And so this comes out to 0.100 minus X molar. This comes out to X molar. This comes out to 0.100 plus X molar. And then we solve this. If we solve this, Ka is equal to, this is what, you should on the test also write the full expression of this in case you make a mistake and get the wrong answer. You can get more partial credit if you actually write this out. And then go ahead and solve this for X.
no application here. It's gonna be the same application. But that's under the control application. And then you're gonna see the right? And then you do the change, which is process. So it will be data
Did you get it? Yes. Yeah, that's, what we're gonna get is we're gonna get x, right? 0.100 plus x divided by 0.100 minus x. And what did you do? You made the simplifying assumption, right? And then we get x is the same as Ka. And so this is a pattern. This is a pattern that I'm just gonna tell you that exists. When we look at the Ka for this, the Ka is 1.8 times 10 to the minus 5 molar. I mean, the Ka is x, and x is going to be 1.8 times 10 to the minus 5 molar. Now, do we have to worry about Kb for acetate? The Kb equation we wrote over there. No, because it's the same equilibrium. It would be redundant. We do, however, have to worry about Kw. Now you look at this. This is 10 to the minus 5 molar. Is Kw going to contribute much addition? No, because Kw at the most is going to contribute 10 to the minus 7, but it's probably going to be way less than that because of the common ion effect. The common ion effect is why we could easily ignore X here, because we got a lot of acetate here. So can we generate much? No, we can't generate too much hydronium because the acetate's going to attack it, right? So it's a common ion effect. If this were 0 and 0, then we could generate more. And so we would stop here. If we're interested in the pH, we stop here, right? Well, this general pattern is what we see in this type of problem. And so rather than looking at it specifically for acetic acid and acetate, we look at it for just any acid, which we call HA. It has to be a weak acid. And so when we have an HA, and this is weak, and an A minus, this is our base, this is weak. Right? An HA A minus mixture, then we're going to come up with a general pattern. We can either do Ka for this or Kb, but not both. We would never do and. Right? Or. Why we do Ka is because we save ourselves one step. We don't have to calculate the POH. And so it doesn't matter if Kb is bigger, we're still going to do it Ka. And so what we'll do is we'll just set up a Ka equation. This is going to be a generic Ka equation. HA plus H2O liquid yields hydronium plus A minus. And so initial, we have HA initial. Water, ignore. Hydronium, we're going to keep it 0 initial, and A minus. And so we have a mixture of weak acid and weak base present at the very start. And then we let this equilibrate, however, so we're going to get minus X plus X plus X. And so equilibrium, we're going to have HA initial minus X. This is going to be X, and this is going to be A minus initial plus X. A molar on those, but let's ignore the unit for right now. And so Ka for this is going to be the hydronium times the A minus divided by the HA concentration. And this is going to be equilibrium, right? And so the hydronium is just X. The A minus would be A minus initial plus X. And the HA at equilibrium will be the HA initial minus X. And then we, because of the common ion effect, the simplifying assumption should work here. And so we just use the SA here. And so what this is going to come out to is X times A minus initial over HA initial. And then what we do is we'll take the negative log of both sides. And then some simplification. I'll finish this later. And then we end up with this equation, that the pH is equal to the pKa plus the log of the base, which is A minus, over the acid, I'll finish this next time, we're just out of time. This is called the Henderson-Hasselbalch equation for Henderson-Hasselbalch mixtures, buffer. This is a buffer. We'll talk about what it means to be a buffer later, but we're just looking at the calculations now. What time do we end at? 12:40? Oh, then we have time. Sorry. Let me finish this. Let's look at the steps here. And so if we take the negative log of the Ka, this is going to equal the negative log of the x, A minus initial, over HA initial. Using the property of logs, we can take the sum of those. So this would be the negative log of x plus the negative log of the A minus initial over the HA initial. And then we're going to add this term to both sides. You know what the negative log is called? It's the power function. You know what the negative log of x is? What is x? X is the hydronium ion concentration at equilibrium. And so negative log of the hydronium ion concentration is the pH. The pH is equal to, the negative log of Ka is just the pKa, and then we'll leave that. But this is going to be plus the log of the A minus, which is the base, over the HA. And these have to be conjugates of each other, right? Those are conjugates. And so what this means is if we use this equation, we can bypass the ice table. For this type of mixture, we don't have to do an ice table. For this type of mixture, all we do is we plug in the initial concentration of each of these. This is initial. So we don't have to calculate the equilibrium because we assume that the common ion effect is going to be very little change in the initials. That's what we did, oh, I erased it earlier. That's what we did with the 0.100. The 0.100 plus or minus x was about 0.100. And so the initial concentrations don't really change much in this mixture. And therefore the same thing here, we just do the initial. And so by using the Henderson-Hasselbalch, no ice table is required and saves time. That's it.
Why is negative log of x equal to pK?
Negative log of x is not the pKa. The negative log of x is the pH, because x is equal to hydronium ion concentration at equilibrium. So, and we assume that Kw contributes very little hydronium, negligible hydronium. So all the hydronium is going to come from this step. There's a Henderson-Hasselbalch. You know, we could have done Kb as well. There's a Kb version of Henderson-Hasselbalch. And so if we use Kb instead, if we used Kb, we would have gotten the POH is equal to the pKb plus the log of the acid to base. And the acid and base, this is going to be initial. So again, you know, both of them are going to give us the same answer. And so we could have used the pKb version, or the Kb version or the Ka version, get the same answer. Okay. Now, the only thing is, since we're always using the Ka version, what happens if the base is much stronger than the acid? And so we'll talk about that next time. So tomorrow in lab, we'll see how a buffer solution behaves.